Okay, this is the second ANCOVA video and the fifth out of a series covering factorial ANOVA and ANCOVA for this week's lesson, and the way I have it set up anyway this year. So this is the steps that you take to be able to run an ANCOVA analysis, kind of moving from assumptions to analyses. So it's similar to previous study, work that we've done. So you're going to check your assumptions first before you run anything. And then if you have interactions, you're going to check your interactions among your independent variables, just like you did when I walked you through on ANOVA, two-way or factorial ANOVA. So I'm not going to go over that again. And so you interactions first, then you examine your main effects of your independent variables to see what their effects are all on their own for each independent variable. Then you either do specific comparisons, trend analyses, post hoc tests, or whatever it is that was significant between, if your interaction was significant, then you're looking at all those little simple mean scores. And if your main effects were significant, you're comparing the mean scores for each level of IV. And then finally, you do add one new thing, and that is what are the effects of the covariates on the study? How much did they matter? And this is unique, of course, to ANCOVA. So covariate can have issues of its own. One is don't just keep throwing covariates into the pot. Sometimes it's tempting to kind of go, well, this could be important, that could be important, and this other thing could be important. Let's put them all in. And the problem is the more covariates you throw in, the more they can kind of water each other down. They can kind of interact with each other. So you want to be thoughtful about what covariates you put in. They need to be important ones, but generally you don't put more than a few into a study. Before you even do it, there should be at least somewhat of a correlation, maybe a 0.25 or a 0.30 correlation of the covariate with the dependent variable. The idea is that if the covariate doesn't correlate with the dependent variable, then it probably doesn't matter in your study for it. So covariates should not correlate with each other too highly. This is called multicollinearity, whenever two variables correlate too high. So you're going to be running a correlation matrix when you run an ANCOVA, and you're going to be checking that your covariates do correlate at least somewhat with the DV, and that your covariates aren't too high with each other. I think most people would say like a 0.75 or a 0.80 or higher would be too high of a correlation between your covariates. If that were to happen, you would probably at least pick one of them and drop it and not include it in the study. The covariates are supposed to be independent of treatment, so they shouldn't be just something that relates to the treatment. There shouldn't be a pattern there, and it's generally collected before the IV is administered. So kind of either be a pre-existing thing like a demographic variable, or something that you give people before you put them in groups. What's going to happen, if you remember, that the covariate actually adjusts the dependent variable score. So one of the issues with the covariate is that you're going to get these adjusted means that can be hard to interpret because it's not the real number. This is kind of like when you do transformations and you take like the square root of something, and now all of a sudden you're looking at something and it doesn't make sense what that number is, just looking at it, at face value. So it's the same thing. That dependent variable value, mean score or whatever you're looking at, isn't the true mean score. It's adjusted based on the covariate. So you just have to remember that. Okay, walking through the assumptions, same as before. Unequal sample size and missing data matter. For this, you look a little bit at the ratio of cases to the independent variables, meaning that you have enough cases for each independent variable. Particularly covariate is going to kind of pull more to the data, so you want to make sure you have a good number of cases in each of your little cells there. You want to make sure you don't have outliers. So this is where you actually do start looking at multivariate outliers, and we will be looking at heterogeneity of regression, it's called, and make sure that we don't have an unreasonable adjustment of the dependent variable happening. So I'll talk about that later, but especially if you have too many outliers, you might have to throw out one of your covariates. Multicollinearity is when the covariates are too highly correlated. So this is the squared multiple correlation of 0.50, or like a regular Pearson's correlation, maybe of a 0.80 or higher, because it's really not adding anything to the formula by adding more covariates. Normality is not a problem if you have pretty good, sample size in all your groups. You don't have a lot of outliers. You're doing kind of the normal, what's called a two-tailed test. That's the default. And if you've got at least a 20 degrees of freedom in your error. Otherwise, if you have a non-normal covariate or dependent variable, and you look at the skewness on those and you find that they aren't normal, then you're probably going to go ahead and run your transformation. And aren't you thrilled? You love transformations. I know, I do too. So just like ANOVA, you're going to have a homogeneity of variance test for Levine's test and hope that it's not significant and that you pass it. There's something called linearity. Basically, this is you want, if you remember back when we did assumptions, whenever you have continuous variables, you want a blimp or a hot dog kind of relationship. You don't want a rainbow, okay? So you want to look at every covariate with each other if you have more than one, and every covariate with a dependent variable in a scatter plot matrix, and make sure you don't have what looks like rainbows or smiley faces. So it shouldn't be curvilinear. If you do, you may try transformation or you may try dropping a covariate. Also, your covariate should just be a reliable measure. So we'll talk about Cronbach's alpha later in the semester when we cover like at the end of the semester. But you shouldn't have a high. If you have a covariate that has a lot of error in it, remember the point of the covariate is to reduce error. So ANCOVAs are sensitive to covariates that have a lot of error in them. So people often will run and they hope to see Cronbach's alphas at least of 0.80 or higher. And then something called homogeneity of regression. This basically means that the relationship of your covariates with your dependent variables should all run the same direction. I'm going to show you a picture here. So this is a picture of covariates that you have and your dependent variable. And on the left here, basically the relationship between the covariates and the dependent variable all run the same direction, right? They've all got this positive correlation going on here. The one on the right has these really unequal slopes. You know, one of them looks like it's running negative. The other two are positive, but at very different slopes from each other. And so if you have heterogeneity of regression, then you really shouldn't run an ANCOVA. I'm going to show you how to do this in SPSS because it's a multi-stepped kind of special ANOVA on the ANOVA that you have to run to check for the homogeneity of regression assumption, and we'll cover that in class when we cover ANCOVA. But I just wanted you to be aware of what it actually is, and I think most people, when they see the picture, they start to go, oh, okay, that's kind of what it means. Your textbook's pretty good about covering this, but it is a more advanced and difficult topic. So make sure you ask questions if you're feeling a little bit lost on homogeneity of regression as an assumption. And everything else from there on is exactly the same on the steps of running an ANCOVA. You're going to run your interaction effects. You're going to be running your main effects. You're going to report your follow-ups of everything that was significant, just like you did the exact same as ANOVA. So I'm not going to run through that again because you've already learned that.